So here we are at futurebuild, looking at the future and new technology. But of course it is the older buildings, and by older buildings, if we just pick out what Mark said there about that building was 2010, we would expect that or think that's new. But of course it's not new, is it? It's 9 years old, and if you were to design that building today, it'd be very, very different to the one that you're describing. So it's a moving thing. Technology changes every minute, and we've got to focus on bringing those older buildings up to speed, because that's where the energy is being used. And it's all very well pointing at BREEAM and all these other low energy targets for new build, but we must look at the older buildings and how we can retrofit those buildings. So let's look at the legacy we have as older buildings, and particularly building owners like Legal & General here today, and British Land and people like that. A building of 4 years old was actually designed 2 years before, so it's actually 6 years out of date already. And as Mark showed there with the mobile phone, is a great analogy. You know, a 6-year-old phone, you wouldn't have it, would you? Throw it away. And also the standards change all the time. And if any of you listened to the previous session, it was very clear that we're not building buildings to the right standard. And even if we are trying to build them to a standard, the builders are not actually achieving that. So we need to look at that. And also from the previous session was about gas. Gas burning is not the future. We do not need to be designing buildings with gas boilers, or even worse, retrofitting with a gas boiler, because we're supposed to be decarbonisation. And because my background is in aerospace, the construction industry just doesn't keep up with the latest engineering. So why retro-engineer? Well, we have a duty of care, if you like, to reduce carbon emissions. But better than that, it benefits the landlords and occupiers by having a smart, I hate the word smart, intelligent building that looks after itself and is in fact very efficient. It's a better workplace for everybody that actually occupies the space. And because of this new technology being applied to an older building, we have a better, reliable building, a building that looks after itself and not relying on Norman going to, you know, turn the light switch on and turn the heating down because somebody's complaining, as we mentioned before. It should automatically know that, and you should expect a building in this day and age to be intelligent. And more importantly, going forward through its life cycle, you're talking about lower OPEX. So let's have a look at other industries. On the left-hand side there you can see, is it left? Yes, it is. Yeah, that's a Tesla car. You can buy one today, go and buy one, it's there. It's an intelligent device. It's not just an efficient machine, it's an intelligent device. You don't even have to drive it, do you? You can just sit in there and let it do it. We don't have buildings like that. Next to that is an A300 jet. That is used by Ryanair, EasyJet on an everyday basis. If you just came here from Europe, then you would have got on one. Look at that cockpit. The pilot doesn't fly that thing, it flies itself. And not only that, it tells you when it's broke. So the engineering in an A300 is already there. It's flying all over the world. The engines are monitored by Rolls-Royce. You know, this is technology that we have today, and we're not applying that to buildings. So let's have a look at how we can apply that technology to buildings. Sorry. If I was to go to a landlord and say, you need to renew your equipment, he would have said, well, it's not worn out yet. I've got 20 years. Sibsy told me it had lasted 25 years. Has anybody got a car that you've had for 25 years? I don't think so. So, you know, oh, sorry, I've gone too far. You know, a rotating piece of equipment only lasts 50,000 hours. A manufacturer will tell you that. So if you're running something 24/7, after 8 years, you must throw it away. You know, periodic inspections and the maintenance that we're doing doesn't capture the plant health. It's just a snapshot. You know, the way that we repair reactively, as you say, and jump in afterwards, is a reaction to ill health. And as you pointed out before, you only go to the doctor. You don't want to go to the doctor. You want to be able to manage something and not repair it, but it doesn't want to break in the first place. You should expect that. I mean, how many of you actually look under the bonnet in the morning before you start your car? Not many. How many of you actually service the thing in line with the service manual? It doesn't, because it tells you when it needs servicing, doesn't it? A Mercedes certainly does that. So why is it that we spend all this money and effort on people using knobs and switches to an overcapacity, over-designed building, when we can actually use artificial intelligence, the Internet of Things, using an M4 platform, we'll come on to that in a minute, 4-pipe heat pumps, chiller condense, instead of using the cooling tower, use it to heat the building with, demand-driven ventilation that measures and only provides the right ventilation for the space, and more importantly, the future, which is 24/7 monitoring and maintenance with no humans, because humans are not reliable. So let's look at where we've done this before. 350 Euston, 4-pipe heat pump, 80% less gas, 40% less electricity. Previously, 2 1-megawatt chillers, 2.4 energy efficiency, replaced with 4-pipe heat pump, 1 small, very efficient chiller. We're looking at efficiencies of 8. Central St Giles, large building, may have seen it in Tottenham Court Road, multicoloured. We're using the condensed water from the chillers there into a heat pump so that there is no heating required. The chillers, because there's a requirement there by the client of heating and cooling, so we get 365 heating and cooling with no gas. 25 Ropemaker, another success where we are using smaller chillers to automatically intelligent interface with the larger ones using lower energy overnight. 110 Fetter Lane, where we re-engineered the CHP to be much more efficient than it was before. Though it was installed, I can't remember how many years it had been there, 6 or so, and never really used properly. 2 Kingdom Street, something that as mentioned, we just won the award for. Demand-driven ventilation, which we'll come on to more in a minute in great detail. So, retro-engineering requires a process, because you cannot jump ahead. You have to do, as Mark said before, you have to go and analyse. You need to go and look to see how that building is operating. And you need the right equipment to do that. You then turn that into an engineering situation, and right at its heart is, of course, connectivity. The internet plays a large part in the new generation. So by evaluating the performance, and we did some detail there, it's this, the way that we do it. Mark's got a different way of presenting it, but that's a basis there where you can see the one against the other. So you're comparing trace against trace. Or you can get really complicated and get loads of metering and looks at loads of things at once. And of course you need a trained eye to do that. So, but once you understand where that is going, you can re-engineer that out. And it doesn't mean that you need to spend a load of money, because mostly it's to do with the BMS. The BMS that's been installed in the building for what, 15, 20 years now, of course is out of date, just the same as anything else is, and these are constant updating. So you need to understand the vintage of the BMS that you have in your building and what you can do about it, and how we can re-engineer the BMS and the control system to be more cloud-based, not stand on an island, talk to the metering, talk to it, and then slowly build in the intelligence. And then you end up optimizing the plant and its control system. And of course, for a very little capex, you've not spent any investment, you can get 20% of OPEX, which is, our numbers are similar to yours, in 20% saving just by studying the building and analysing it. And that analytics is something that can be, and as Mark is saying, you can get as a service, but if we move that analytics into the wider world and we think of the Internet of Things, our goal has got to be, this analytics is a millisecond thing, that the computer is completely always analysing 24/7 the nature of the building and calculating what input it requires to keep it efficient. So the first thing you'd have to do as well, and I'm sure you understand this, Mark, is that you need to do a thermal model. And where we're doing this thermal modelling is that you must not forget that if you've got 2,000 people in the building, then you've also got a heat source. So you need to be looking at what is happening on your floors. If you've got an unoccupied floor or an occupied floor, you have a different heat and cooling aspect. And if we have an holistic computer system looking at that, then we can optimize the plant efficiently. So in our modern systems, we need to be future thinking. And Industry 4, is anybody familiar with that term, Industry 4? Yeah, okay, well, we've got one person in there. Industry 4 is the fourth industrial revolution, which we're in the middle of right now. And most of our industry here in the UK and in Europe uses sensors, for example, that interface to the cloud. No BMS, the BMS is actually on the cloud. So the control systems, car manufacturing and aircraft manufacture, pretty much everything is on Industry 4 right now, but the construction industry isn't. So we need to look at how we can move that into our new buildings and in retrofit into our old buildings. That allows us to have artificial intelligence, connected maintenance, and the decasification. I know I keep banging on about that, but when you think that a heat pump is got a multiplier of 4 or 5 on the electric, and a boiler at best is 96% efficient, and that's at the end of the day what we're trying to do here is reduce our CO2 production. And if you're not familiar with the N4 platform, the N4 platform is a language that will talk to all BMSs. So if you've got a Trend system or you've got a Johnson system, whatever system it is, it can now all talk on the one platform. So you don't have to rely on the manufacturer anymore. You just use an M4 platform. So, coming back to the analytics for a minute, in order to move forward, you need to start reinventing the topology, which is using the M4 platform to give you the intelligent ventilation, because you can't do that from the standard BMS. It hasn't got the ability to do that, so you need to plug in another level of intelligence, which is this N4 platform. By using hybrid heat pump technology, if you then specify that N4 platform to be in the product when it's delivered, then as you take one out and plug it in again, you're plugging it straight into the N4 platform and not the BMS. And the reason you need to do that is that the BMS becomes a slave. The machine is interacting with the cloud, with the N4 platform, and it will tell the BMS what to do. So you don't have to strip it out, you just need to reuse the older BMS. Intelligent chill water control and optimization. This is where we're controlling chillers to be intelligent, so that they only load up or unload depending on what they're actually being asked to do. Nearly every chiller that you have in a building sits on its own intelligence right now, which was programmed in by the manufacturer. And of course, along with that, you need your intelligent hydraulics, which is variable speed drives. You need to make sure the right water is going through everything, and it's being controlled every millisecond, not every now and again when you go and have a look. So let's just recap. We want to establish the infrastructure. Make sure you're buying a new kit with a backnet or direct to the platform. Always make sure that the building is connected with a fibre optic, so because in the future, if you've not got a fibre optic, you can't talk to it. And let's have a look at the detail of the analytics that Mark was picking up. If you look at the blue line in that CO2 vent system, is how the air handling unit used to operate. It came on in the morning, it ran all day, it went off in the evening. After the retrofit of CO2 controls, you can see that it actually follows the occupied load. The air handling unit only operates to provide ventilation to the people in the floors. You can see it doesn't actually start till 11 o'clock because the CO2 hasn't built up. And you can see that you know, it goes off at lunchtime and then starts to die and build up again, just as in response to the occupied load. You can see that the 40% energy reduction in the fan there, just by intelligence. This is a 4-pipe heat pump, for those of you who haven't seen it, that heat and cool at the same time. Same machine. So there's no other medium required apart from electricity. And last but, it's not last, we would hate taking questions, but the last thing I'd like to talk about is our chiller flight information system, where we're looking at real-time monitoring of the health of a chiller. Why a chiller? Because it's expensive to replace. And if we bring in this intelligence into our chillers, then we get an early warning of failure, auto shutdown, and really saves the thing from smashing up.